Uh,
basically control access to the critical section. Okay, so semaphore uses atomic concepts. Okay, to control access to critical section. What is meant by atomic? Just for the sake of revision, we talked about it before already. Now, atomic is referring to treating a set of operation as a single operation. Okay, so basically we didn't allow interleaving, we did not allow interruption during execution of those sets of instructions. In other words, if, for example, there's an interrupt happen, so the processor will finish those set of operation first before it handles interrupt. Well, we have different types of.
Okay, so those are the very basics of semaphore. Basically, yes, we use it to synchronize access. And in any semaphore implementation, there's only three functions. Okay, one is the initialization of the semaphore value. Second is wait on that particular semaphore. And third is signaling from that semaphore. Okay. And then it says those operations are atomic operations. In other words, execution of those operations, once it starts, it has to finish. We don't allow any preemption. Okay. In execution, those operations of semaphore, basically the initialization, wait, and signal. Okay, and then here after that, it introduces you to the three, how should I say, types. Binary and counting are basically, yes, the two different types of semaphore. And then we say another one, we say complex semaphore. Now, complex semaphore is not actually a type, it's actually a different way of implementing the same concept, which is also semaphore. But we implement it differently, not too much different, but we'll go into that detail also in this particular video. Okay, so focus and we'll continue.
Of semaphore, we have binary semaphore, we have a counting semaphore, and we also have a complex semaphore. Now, what you see here in the yellow and the blue box are the concepts of the simple semaphore, basically. Okay, the wait operation, basically, before we access the critical section, we issue a wait. Okay, waiting on that semaphore. And in the wait operation, what we do is we simply check if the semaphore value is not zero. In other words, no one has accessed that critical section. Okay. On the other hand, if the value is positive, then only we go inside and then we decrement that value. Okay. So if that value is type, I think we talk about generation later. Okay. And then the signal operation is very simple. Once we issue signal, basically once we are done with accessing the critical section, and what we do is we simply increment the semaphore value. And what we do is we simply increment the semaphore value.
So do you get the point? Right? When do we issue wait and when do we issue signal? Right? So we wait on a particular semaphore before we access the critical section. And then we issue signal once we are done with the critical section. Simple as that. Okay, so what is generally what does wait do? Well, we check on that semaphore. Okay, meaning if the value is not zero, some positive, okay, then what we can do is we can enter. That's why we say while s is less than or equal to 0, semicolon, which means what? We keep on looping on the while s is less than or equal to 0. However, once the value becomes greater than 0, which reflects the availability of the resource that we want to access, so we will go ahead and access the resource. At the same time, we decrement the S value. So the S value here reflects the availability of the resource. Okay, because the resource that we want to access, possibly maybe our computer system only have one of that resource, or it may have more than one. Okay, so the value may be 1, 2, 3, 4, depending on the resource availability. Understanding? What about the rest? You guys okay? Hmm. Can someone speak up? Your understanding, I would like to listen. Okay, tak apa. We'll proceed. And then what about signal? Well, signal is once we are done with the resource, and once we are done with it, what do we do? Means the resource is free, right? So what I do, if you check the, it's not very clear here because of this. Yeah.
Okay,
Okay. Once we are done, we increment. I mean from the previous slide, not this one, right? So we say signal on S. We simply S plus plus, meaning the resource is now available. Whosoever wants to go in and access the resource, you may, because the others will also be waiting on that semaphore. Okay, that is our simple semaphore, right? We haven't, in general, we haven't talked about the binary, counting, and complex. By right, we can easily make this into a binary semaphore simply by having our S value equal to 0 or 1. Then it's binary, meaning that reflects there's only one resource available of that type, okay, on the computer system, meaning there's only one resource, whatever that resource is. Okay, is it either a file or even a hardware that we need to access, whatever it is, okay, it's a resource, okay, or just a variable or data that we want to access, okay. So kalau variable to definitely there's only one type, sorry, one variable of that particular data, then logically the S value should be initialized to 1, means it's available. But once somebody accessing it, then we decrement it to become 0, meaning someone is using it. And then when that someone is done, it should issue a signal saying that, okay, I'm done with it. So S value plus plus, so the S value becomes 1. Now we go into complex semaphore.
And what we do is we simply increment the semaphore value. Okay, complex semaphore. Complex semaphore is slightly different from the simple semaphore. If you remember, in the simple semaphore, when we issue the wait operation and we check if the semaphore value is negative, right? In other words, it's 0, sorry. Means the resource that we're looking for or the critical sections that we want to enter is currently being utilized by another process. So what we do, we keep on checking on that, keep on looking, which means like it's like calling on that operation. So we are actually utilizing the CPU time. In complex semaphore, the approach is slightly different. Basically, we just check if the semaphore is 0, then what we do is we block that process for that particular semaphore. So we have a queue of processes blocked on that semaphore. And on the other hand, if the value is 0, what we do is we simply decrement the semaphore value, which means the process can immediately access the critical section, okay, of the code. And then as far as the signal operation, once the semaphore is done, it checks if the semaphore value is equal to 0 and there are processes waiting on that semaphore in the queue, which are process blocked on that particular semaphore. So we will wake up the process at the front of the queue and let it access the critical section. On the other hand, else, if the semaphore, if no other process are waiting for that particular semaphore, then we simply increment the semaphore so that when other process that comes in later who needs to use that critical section, it will issue wait, and then it will see the positive value and it can access the semaphore, can access the critical section. Well, we talked about the positive value and it can access the semaphore, can access the critical section.
Okay, guys. Now this is on complex semaphore. Now, can you differentiate between the earlier semaphore, or we can simply say that the simple semaphore and the complex semaphore? What's the difference? Anyone? Both concerns how we implement them. I mean, both complex and simple semaphore wants to do the same thing, basically to synchronize access to critical section, which is basically our shared resource, the critical section. But both implemented slightly differently in the wait and signal function. So what's the difference? Can you see the difference? Anyone? Don't be shy, speak up. There's no wrong answer. Increment and decrement. Can you elaborate further? What is it? It's like why, right? We are the why people. There's always a reason behind something. So why do we do that? Why do we do this? What are we doing? And why are we doing that? Now, in the previous simple semaphore, okay, let me go back to the slide so that people can see.
The process that utilizing, remember that value is a type.
Okay, you see, if I am a process, I issue wait on semaphore, any particular semaphore that I define. And then once I execute the wait function, it says wait as. And then the first line of code inside wait as is while s is less than or equal to 0. Now, if this statement is true, meaning s is less than or equal to 0, what do I do? The process, it keep on checking while until this value becomes some positive value, 1, 2, or 3, or whatever, right? Then only I will surpass this while statement and decrement s minus minus. So what's the we can say problem here? Do you guys remember the concept of busy waiting? Do you remember your concept of polling and interrupt? Why is polling bad? From your micro P or embedded system class. Why don't we like polling? We prefer interrupt in general. What is meant by polling, if you remember? Yo, no one remember. Polling tu P-O-L-L. Huh? Because when you pause it, you keep on checking, right? Here, my code, okay, at this line here. Oops. Kenapa tak ada apa-apa ni? Oh, tak masuk. All right, here, this line, right? So once I execute this wait operation on the semaphore that I want to access, so my code, once it goes into the wait function, it executes this line. So as long as S is 0, okay, or some negative value, so what will my process do? It keeps on executing this instruction while S keep on checking the S value. Is it still 0? Is it still 0? Is it still negative? Is it still 0? Is it still less than 0? Is it still less than 0? Checking. So what happened? I'm utilizing my CPU, right? Unnecessarily. Well, the code works, but I keep on checking. It's like somebody comes to your house, is asking, boleh saya masuk, 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 kan? Ya, kita tak boleh, I'm busy right now, kita boleh saya masuk. Until you say, okay, you can enter now. Instead of, kan? So that's what happening here. This process keep on executing this line of instruction. You see that semicolon here? Yeah, kan? That's why. So you keep running this instruction. However, and then once the value becomes S is equal to 0, or S is equal to some positive number, then it will pass this while loop and execute S minus minus, meaning it get access to the semaphore already. And now let's look at the complex semaphore implementation. Okay, complex.
I think we talked about binary. On the other hand,
all right. If you look at this one, hello. Oh, ada. Laptop saya ni memory tak cukup. All right. Now, on this complex semaphore, on the other hand, what do? Once we enter the wait, we say if semaphore S is equal to 0, what do? Well, inside my computer, I have a queue. Okay, any process who is blocked on S, they are blocked. Okay, meaning they want to access a particular shared resource which uses semaphore S as the semaphore controlling access to that particular shared resource. So once they execute wait on that semaphore and they see that the S value if semaphore S is equal to 0, meaning the resource is not available. So what I do, we put the process in a queue. And then if there is another process also waiting on S, it will be next in the queue like that. So it won't keep asking, is it still 0? Is it already positive? Is it already positive like the previous implementation? Okay. Understanding? So once we put them in the block list, so what happened? When will those process block on semaphore S will be able to access the the resource that they want to access? The answer is being done inside Signal. Okay. The process which is currently accessing that particular shared resource, once it's done, it will check if semaphore S is equal to 0 and there is a process on the wait queue. So what it will do, it will wake up the first process in the queue waiting for that process. So the one at the head of the queue will be woken up from the waiting queue and get access to the resource. And it maintains S is equal to 0. Understanding? On the other hand, if that particular processor is currently using the resource is done and it check if semaphore S is equal to 0, but then the queue is empty, meaning no one else wants to use the resource at this point in time. So it goes ahead and increase the S semaphore by 1. So now the S value becomes 1. So whoever comes after that issues a wait on that semaphore, it will see S is not equal to 0. So it directly get access to the semaphore and decrement the S value. Okay. So the difference is complex semaphore does not enforce busy waiting on that particular semaphore that any process wants to access. Macam mana saya nak padam ni? Banyak sangat sunting kan? Clear all. Alright. Understanding? Is my explanation better? I would appreciate if people wants to speak up and speak up your mind. Channel said he's feeling good. Would you like to speak up? Mr. Quay? Because this is very important. So if we go deeper, we can say that. Now, if we say S, let me again activate my pen. Okay, if I say S, what does S equal to 0 means? What does it means? Anyone? Belum paham. Okay, let me give you guys an analogy. Long before when I was doing my study, my lecturer used to give this analogy of a public toilet, right? Now, what's the basically the general procedure for us to access public toilet? We go to the public toilet and then we pay our money, right? Once we pay the money, then we go inside. Maybe there are some 5, 6, 7, 10 of toilets available. Now, once we go inside, sometimes we see all the doors are locked, meaning someone has already came in and paid before us, and they are accessing those public toilet, which are our resource in this particular case. So what we do, we have to wait there. And okay, so now we change the scenario a bit. I want to explain about the concept of semaphore here. Okay, the concept of semaphore is that if we change the scenario of the public toilet, we say, okay, what we should do now, the person in charge taking care of the public toilet, he should keep some tokens. Okay, keep some tokens. Let's say if the toilet available is 10, sorry, if there are 10 available toilets, which are number of resource, then that guy should keep 10 tokens. Okay, meaning, so when we, the customer who wants to access the public toilet, we go to him, wanting to access toilet, then he, as the manager of the toilet, he can see whether the toilet is available or not based on the number of token available with him. Okay. So if the token is available, any number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then we pay our money, we go in, then we don't have to wait. We know the toilet is available. We go in. So once we go in, what do? Okay, the moment that we go to the public toilet just now, we are basically issuing a wait on public toilet, or wait on S, wait on our semaphore. Okay, we are waiting on that token controlling our public toilet. The public toilet is the resource. The token is our semaphore. Okay, so we check on the number of tokens available. If the token available is 10, then I know there are 10 available resource inside. So I pay my money, I can go in and use any of those one resource. And the moment I go into the toilet, what should I do? I should lock the door, right? So the operation of locking the door is actually decrementing the available resource, which is decrementing the number of tokens, right? And then once I'm done, I go out from the toilet. Okay, before I go out, I open the door. Once you open the door, basically the number of token again increase. That is signal. Okay, so does with your computer resource. Once you're done using that resource, you issue a signal S++, right? So now the resource is again available. That token being kept by that guy who's managing the public toilet. So that guy becomes our operating system, managing the semaphore, okay, managing the token. I think that analogy gives you a clearer idea on what semaphore is. So the semaphore is the token. Okay, the public toilet is the resource. In our case, whatever the resource is that we want to access, and S is our semaphore value, which is our token. Boleh faham tak tu? Understanding? Yeah, this concept is quite tricky. Okay, let's proceed with my video.
And else, if the semaphore, if no other process are waiting for that particular semaphore, then we simply increment the semaphore, so that when other process that comes in later needs to use that critical section, it will issue wait, and then it will see the positive value, and it can access the semaphore. It can access the critical section. Well, we talked about semaphore. Well, the three operations. Okay, we need to initialize the value. Okay, depending on the type of semaphore. If you're binary, then the value is 0 or 1. If it's non-binary, okay, counting semaphore, then it will be some positive number or 0. Okay, and then the values of semaphore. Okay, we talked about already. Now the types of semaphore, we have standard semaphore, which is the simple semaphore, which is busy waiting on the wait operation, keep on checking, right? And then for the complex semaphore, we basically send the process to block, stay waiting on that particular semaphore if the resource is not available and the wait request is issued by that particular process. Okay, now so we'll do a bit of animation to illustrate the concept of semaphore. Assume that we have a scenario inside a clinic, right? Where you go to clinic to get the service from the doctor, right? So when you go to the clinic, but this clinic is special, it has no receptionist. But on the door of the doctor, there is a number indicating the availability of the doctor. Zeros indicate no doctors inside. Or there is a patient inside with the doctor, and 1 indicates the doctor is free to meet the next patient. Okay, so you as a user, okay, wants to meet the doctor, not you as a patient, right? Actually, if you want to compare this to the computer, you are actually the process and the doctor is the shared resource or the critical section that we need to access. Okay, so if you see a zero, so probably the doctor is not there yet. And then after waiting for some time, it arrived and the doctor changed the value from 0 to 1, indicating his availability to meet the next patient. Okay, so the fact that you were there, you had already issued a wait, right? So once the value changed to 1, where you've been checking while S is less than 0, okay, you keep waiting there and checking, waiting and checking. So once the value changes from 0 to 1, what you do, you go inside. Yes, like that, you go inside. Okay, and close the door. So you are accessing, you are meeting the doctor, right? And change the semaphore value, the numbers on the door to 0, indicating that there is a patient inside, right? And once you're done, you come out. Okay, you come out, and what you do is issue a signal saying that the doctor is, sorry, not you, the doctor will issue a signal indicating his availability for the next patient. And then the new patient comes in, the next patient, you want the one in red color. Okay, it's all, he issues a wait. And of course, since the doctor is available, enters immediately and go inside. And the value is changed to 0. The doctor is busy seeing the patient. And then as during his seeing the doctor, some other patient comes in, patients number 2 and patients number 3. All right, so they have to definitely wait, and that's how it goes. All right. Now we talk about this during
Okay, now, okay, once the patient with red color goes inside, okay, so S value now become 0, right? And then what happened when the green patient comes in, P2? What happened to the S value? Is it still 0? No, you're waiting on S. Previously, the value was 1, right? Here, I mean. Okay, when the red patient comes in, the doctor is free. So meaning the doctor is our resource that we want to access, that the patients wants to access. So the patients are the processes. The doctor is the resource. Okay, so once the patient comes in, meaning is issuing a wait on the doctor, waiting for the doctor. But in this case, the doctor is available. So he goes in, executing the code while S is less than or equal to 0. Well, that is not true. So immediately it go to S minus minus. Then, so S become 0. That's what happened.
saying that the doctor is, sorry, not you, the doctor will issue a signal indicating the doctor is available, enters immediately.
Okay, as you can see, now before this green people is there, right? So once you enter, the value changes to 0 because the doctor is not available for other people, meaning the first process, the red process, is using that particular resource. Okay, the doctor is treating that patient. So the doctor is not available. And then while the patient is being treated, okay, while that process is using the resource, some other people comes in. And those people comes in, basically they are issuing a wait on the doctor, issuing a wait to use the resource.
And the value is changed to 0. The doctor is busy seeing the patient. And then as
Okay, two other person comes in. P2 issues a weight. P3 also issues a weight, while S value is less than or equal to 0. So now what happened? The value changes or not? The S value. Anyone? When the green patient comes in, when the blue patient comes in, does our S value remains the same, which is 0 right now? Okay, channel says the same. Yang lain macam mana? S remains 0, yeah. Okay. So once that patient goes out, meaning the red patient who is now with the doctor, once it goes out, what happened? It will issue a signal S++. All right. So among the process waiting, green and blue, who will get access? Once the red patient goes out. Whoever managed to execute that while S less than or equal to 0 first. Right? Why do you say green channel? P2 is after P1. Okay, issuing a weight on S. But do we have a queue keeping track of who issue weight first? The code doesn't say so, right? So based on the code, we have no idea P2 or P3 comes in first. P2 or P3 issues a weight first on semaphore S. This is simple semaphore, different from complex semaphore, where we have a queue. Okay, those comes in, they wait on that queue. So on simple semaphore, based on the code, we can say that any of the two process, because both are now polling on while S is less than or equal to 0, green and blue. So whoever managed to check that value first, once it's incremented to 1, so that process will goes in and decrement S minus minus. That's what will happen in simple semaphore.
During his for actually we talked about it already, right? Just to revise, if we have semaphore,
On the other hand, if we are using complex semaphore, then yes, green will go first because they are kept on queue based on first come first serve just now. Whoever arrives first will be at the head of the queue.
Concept is similar to the standard semaphore, but implementation is slightly different. I repeat here that once we issue a weight in the queue,
I think we talked long enough on this. Now,
any other
question, right? Back to my question earlier. So we say that. So what does it mean S equal to 0? And what does it mean S is some positive value? And what does it mean when S is negative value? So when S is positive, what happened? S is 0 means resource is available or not available. Toilet is available, channel says, right? S is 0, toilet is not available. S is positive, toilet is available or resource is available. What about S is negative? What does it mean? Is it possible for S to be negative in simple semaphore? Yes or no? Pang, how do you explain that S become negative in simple semaphore? Let's look at the code. Okay, this was simple semaphore. Is it possible for the process to be less than 0? If it comes in and the resource is not available, you keep on checking saja. You never decrement it. Right? So chances are, we can say it's almost impossible for S to be negative in simple semaphore, code-wise, because none of the process will go in and decrement S minus minus. Okay, once they comes in, theoretically, yes, okay. But implementation-wise, we see that that is not possible to happen. By right, we can simply check on S equal to 0. Is it not available? Okay, but on complex semaphore, yes. Right, because when it comes in, it checks the resource is not available. What happened is block on the queue. Okay, so back to my question earlier, what is meant by negative value of semaphore? What does it indicate? A negative value on a semaphore indicates, yeah, queuing for toilet, okay, but in general, but negative that value reflects the number of process waiting on that resource. Okay, if it's negative 3, meaning there are 3 process waiting for that resource in queue. All right.
The block on the queue. Okay, check. You do not increment the value as you did in the standard semaphore, but instead you just wake up the process in the queue and let them use a critical section, and the value remains 0. On the other hand, if there are no process waiting, then only you will execute the else statement, which is you increment the semaphore value. So that would allow any other process that comes later to see that here the resources available, so they can actually easily access the critical section. All right, now we talk a bit on monitors, right? Now, monitor and is another solution to another software solution to critical section. The idea is what we do is we encapsulate the critical sections by means of creating a class. Okay, so same goes here. It also has functions to basically manipulate access to the critical section. One is to initialize the value, and then to request for access, and also to release the access. Right? But of course, the fact that it is a class, right? As compared to semaphore, where each process can invoke the function waiting signal. Now, this request and release function belongs to the class. Okay, so
Yeah, guys. So basically, my focus is on semaphore. Okay, you can read on the monitor part from your textbook and a bit of my notes on that part. Okay, implementation wise, My concern is semaphore because that's what you guys will be using for your um, assignment later on. And considering you guys are computer engineering student, I think that those are more relevant. All right, we take a break for how long do you guys need before we go to the next part? Doing some exercise on semaphore. Give you guys some 5 minutes or maybe 10. Okay, then we continue. Okay, 10 minutes, 10 minutes. What?
The data being manipulated by the process sometimes comes from another process. Okay. So what we want to
Use semaphore to control access to chat resource. Okay, you watch this video and we'll explain the scenario and see how we go about basically assigning semaphore to different. Now, at any point in time, if you're confused, please stop me. Do not wait until the end because it's quite complex. Okay, kalau dah sampai ujung, then I need to rewind. Rewind becomes quite not easy. Okay.
Okay, here we'll do a small exercise on using the semaphore. Basically, we have three processes which basically they want to input information. However, they are sharing input device. Okay, as you can see, the data being manipulated by the process sometimes comes from another process. Okay. So what we want to make sure is we want to make sure that accessing to the input device are mutually excluded. Okay, so in other words, we want to make sure that when a particular process access an input device, then only that process should access and the other should not be allowed to access at the same time. Secondly, is we want to enforce a synchronization. If you look into the code of each process, we can see that, for example, this particular process right here, process number 1, when it wants to add ky equal to a1 plus c1. Now, a1 is coming from p1 itself. However, c1 is coming from process number 3, right? So logically, before it could add the value C1, it has to wait that process number 3 has already acquired, or we say updated the correct value, right? So there's an example there. Okay, so we see that C1, okay, for process 1 to proceed with adding y equal to a1 plus c1, so it has to wait input from process 3, right? So they can do the addition. Now, same here that when it wants to print the value of x, well, x is coming from process P2, right? So it has to wait for x coming from P2. Now, at the same time, process P2, which does the addition of x, we see that it does w is equal to b2 plus c2, right? So b2 is of its own, but c2 is coming for process 3. So again, it has to wait for b3 for this case. And then for process b2 to proceed, adding z, c plus y plus w. Well, it has w from its own, y it has to wait from process 1 right here. right? And then Z is coming from process number 3. So we can see that things has to be synchronized properly so that the final value is correct. Okay, so that's what we want to achieve. Okay, so we see that C1, okay, for process 1 to proceed with adding y equal to A1 plus C1, so it needs to input from process 3, right? So they can do the addition. Now, same here that when it wants to print the value of x, well, x is coming from process P2, right? So it has to wait for x coming from P2. Now, it has W from its own dependencies here, right? And well, B1 is coming from process number 2, so that's like that. Okay. So we want to use semaphore as the mechanism to ensure proper access to the critical section. Okay. So just for revision, we need to remember that to use semaphore first operation, we have initialization. Okay. The second operation of semaphore is we have wait on semaphore. Okay, basically, if the wait value is 0, that would mean the process which issues wait on that particular semaphore will wait, right? Or if the value is positive, then it will decrement it, right? Now, another operation is signal. Basically, when process issues a signal on a particular process, what it does is it will increment the semaphore value. Okay, so what we do now is we want to rewrite the code with semaphore to enforce mutual exclusion and also synchronization of access. Now, we had already said that we need a semaphore for the input device, right? As you can see, all 3 processes needs to access to the input device to get some data. So we're going to call this particular semaphore as semaphore S. Okay, and this semaphore we should initialize it to the value 1. Well, the reason behind is we only have one input device, right? Which is being shared by all 3 recipients. So now let's rewrite the code. Now for process 1, basically, in fact, for all process, before they access the input device, of course, we need to do a few things. So let's do that, okay? So we already have our semaphore to control access to the input device and initialize it to 1. The fact that we have one input device and it is ready right from the beginning. It means the device is there, right? So any of these process which issues a wait first on that input device, it will decrement that value from 1 to 0 and then access the input device. And once done, it will issue a signal which again increment the input device value semaphore to 1, right? So we have for process 1, we have wait on semaphore, and then we get the code for process 1, which is input A1 and A2, sorry, right? A1 and A2. And then when it's done, it's signal S. Now, same goes with process number 2. It also issues wait on semaphore S, and then encode the 1 and the 2, right? And then signal on S, the input device, right? It has nothing to do with informing the other process that those particular data is ready for access. I mean, talking about synchronization, right? We discussed earlier. For example, to do addition of those as y equal to A1 plus C1, so it needs to wait for the input from C1. Okay, so we need more semaphores to control those. Okay, so for now we have only semaphore to control access to the input device. Okay, so for the synchronization part, let's see what are the semaphores that we need. Okay. Well, if you look into process 1, what does it needs is needs to wait for this particular value C1, right? So we need a semaphore for C1. And then we also need a semaphore for X. So we name it as X semaphore X. And then we have for process 2 needs to wait for C2, right? So there's a semaphore on C2, and then it also needs a semaphore on Z and Y, right? And then for process 3, it needs a semaphore on A2 and also semaphore on B1, right? Now, having said that, now what should we do next is all semaphores needs to be initialized, right? So what value should we initialize our semaphore to? Well, in the beginning, when we issue semaphore S for the input device, we initialize it to 1. The reason behind is at the starting point, we do have one input device resource which is being shared by all 3 processes. So any process issue wait first on that particular input device will basically recommend that semaphore to 0, right? As we mentioned earlier. Now, for the case of the following semaphores, which is meant for synchronization in this particular case, right from the beginning, we know that those values are not there yet, right? So logically, we should initialize those values to 0. For example, SC1 was not there in the beginning, okay, unless P3 executed the first line of code, which is input C1 and C2. So we want to do SC1 equal to 0. So does SX, right? SX should also be initialized to 0, right? It's coming from process number 2, that is the line of code. Then SC2 should also be 0. Basically, all of them will be 0. SC will be also 0. And then SY, as we initialize to 0, and then we have SA2 and SP1 for the first one. So we have all of them initialized, right?
Okay, guys, any questions so far? Are you guys okay? Pakcik-pakcik dan makcik-makcik sekalian. Any questions, anyone? You guys feeling great, feeling bombastic? You guys okay? Can follow the logic? Why do S equal to 1 and the rest is equal to 0? Initialization. Saya suruh tanya, you tak nak tanya, saya tanya lah. Why do semaphore S was initialized to 1, but semaphore SC1, SX, SC2, and the rest are initialized to 0? Back to basic, right? Semaphore represents what? Availability or non-availability of the resource that you want, right? So at initialization point, what does semaphore S represent? Semaphore S represents our input device. So is it available at the beginning? The answer is yes. So the value is 1. What about the rest of the data, SE1, SE2, SX? None of those are available yet. So that's why we initialize those to 0. Okay, so always remember the basic. What does everything, what's the purpose of something? Then we can do the thinking of what value to initialize those.
Well, the other thing we need to make sure after initialization is issues weight and signals on those semaphore. But we need to be very careful to make sure that our combinations of weight and signal does not lead to what we call deadlock. In other words, the process should not be a situation where they end up in endless waiting. Okay, one process is waiting for the other, while this process also waiting for the other to respond. Basically, one of them cannot proceed. Okay, so how do we achieve that? Right? Okay, so now we've come to the more critical part, that is we want to make sure that we want to issue weight and signal on those semaphore, but we need to make sure that it doesn't end up in what we call a deadlock. Okay, so let's do that. Right? Now, if we look at process number 1, right? Proceed with the second instruction, which is y equal to a1 plus c1. So it needs the value for c1. So it needs to wait on c1, right? So it needs to wait on semaphore c1, right? Now, this semaphore c1 is coming from process number 3. We look at process number 3, which is also waiting on another value, which is needs to wait on SA2. Okay, looking at this, E1 needs the value from C1, which is come from process number 3. At the same time, process number 3 also needs A2, which is coming from P1. Now, by right, the value C1, which is needed by the value C1 is needed by process number 1 is executed in the first line of P3, right? So before P3 actually waits for SA2, we should actually signal, right, that it has the value C2 ready. So anyone's waiting on the value C2. Okay, so signal on C2, right? Now, the same goes with process P1, right? Before issues a wait on C1. By right, it also holds the value which is needed by the other process, right? Which is A2. So A2 is ready before it executes instruction y equal to A1 plus C1. So by right, E1 should also signal semaphore A2, right? Okay. So going back to P3, once P3 get A2, so it also needs the value B1, right? So it needs to also wait on process B1. Now, process B1 is coming from process number 2, right? If you look at process number 2, is B1, then process number 2 itself needs to issue a wait on SC2 just now, right? Okay. So, and of course, in this particular case, same like our earlier discussion just now, as far as B1 and B3, there is a waiting by both process, right? And both process hold some data needed by the other guy. So, process B1 also need to signal the value it holds, which is as B1, which is needed by process 3. And it also is B2 being B2, right? What about process C3 here? Well, it already signal SC2, but just now SC1 needed by P1 was not there. So yeah, initially the first signal is meant for signal C1 just now, but then I mistakenly write SC2, and your SC2 is also needed by process number 2, right? So that's what we have. So we are done with this instruction right here. A2 and B1 is also been signal, right? A1 and C1. C1 as A2 has been signal. We don't have SA1, and then SB1, SB2, B1 needed by P3, B2, well, we don't have that. And then we signal SB1, we wait on C2, and then we have an input one. C1, C2 both are needed by P1 and P2 respectively, so we signal both S1 and C2. And then P3 cell waited on SC2 and SB1. Okay, the fact that they all had for the second instruction, right? For example, the process C3, process P3, I mean, color, right? So we have it has waited on A2 and B1, so then it can execute in session Z is equal to A2 plus B1. Now, do we have semaphore on Z? Since we have a semaphore in Z, so Z is calculated. So P3 issues a signal on that semaphore. In other words, the data is ready for data Z is ready, right? Semaphore Z. We call it that, right? And start process P3. And then in process P2, it can now already wait for SC2. B2 is coming from its own. So what it can do is issue W equal to B2 plus C2, right? That instruction now is, we have a semaphore on W. Well, the answer is no, right? So we don't have to issue a signal on W. Nobody is waiting for that value, right? B2 is, W is only being used by B2. I mean, it generates that value. And then it can issue the instruction X no, before that, all right? Before that, okay, before you can execute instruction X equal to Z plus Y plus W, well, definitely it needs to issue the wait, right, on those values. So W it has in hand, but Z and Y, it needs to issue a wait on those. So wait on Z, sorry, SZ, and then a wait on SY, right? Okay, then we can do the calculation for x equal to z plus y, then plus.
Guys, no questions so far? Okay, tak okay ni? Diam aja. Alright. Saya tanya tak boleh jawab tadi. So what's the principle here? After you do initialization, you have to check for what value that you're waiting for. At the same time, you should check what are other values that you hold are being weighted by the other process. So in that case, the value you are waiting for, you should issue a wait, but the value that you have, once you have a particular value being weighted by another process, you should immediately signal that value. Okay, before you issue a wait on the value that you need. Okay, signaling out the value that you have before you issue a wait on the value that you need. That is very important. Okay, chances are if you don't do that, if you do the reverse, you wait first and then you signal what you have, then there will be deadlock. No one could proceed. Okay.
Exactly. Right, and then for P1 has the data it needed, so you can issue the instruction y equal to P1 plus P1 plus C1, right? So we waited on C1 already, so now it has calculated the equation. So what you can do is you can signal
Y
as y, right? And also let's signal as y, and then it wait on x, right? It should wait on as x. Okay, at the same time, x is needed by P1, and so P2 needs to immediately signal as x, right? And here, once it signals x, and then P2 is done for P1, if you signal as x, then it can print x. Now we have the whole process done. Okay. So what we can say here is that the rule of thumb is we tend to be careful on how to initialize the value, and secondly, in setting the wait and signal, we need to be careful about deadlock. And how do we avoid that? Basically, when a process has a data ready, it should immediately signal that data out if we have a semaphore on that data. Okay, before it issues a wait on any other data. Okay, you should signal first whatever data you have. Of course, data which is where a semaphore defined on that data. If there is no semaphore defined data, then of course, if you signal is not a valid operation anyway. But once you're done with signaling, then whatever you need for the next instruction for your own process to calculate, then you should wait on those values. Else, you will go into deadlock.
So guys, you guys get the tips already? Number one, initialize, right? How do you initialize? Well, remember what is initialization? Semaphore is meant to represent the resource that we want. The resource that is shared by so many number of processes, right? So initialization means that the at the beginning of time of your process, then what is the available number of that particular resource? That should be the value of your semaphore. Okay, if there are two resources of that type, then it should be 2. If there is 1, it should be 1. Well, if it's not available at the beginning, then it should be 0. All right, and then as you goes down, once you see any lines of code, okay, that manipulate some resources, so immediately, well, human, we normally we try to look for what are the data that I need. Okay, but do not forget, you should also take care of what are the data that I have, which is needed by others. So immediately once you have your data, you should signal out the availability of that data or resource, and then you issue a weight on what you need. In that way, your semaphore will be proper, so you can avoid deadlock. Okay, I think that's all for today that I have. Unless anybody has any question in this particular regards, then I can address them. Now, with regards to your midterm exam, I tried to book on, that was a Monday, the week after the semester break, but so far I haven't get a response. Maybe the person in charge is involved with flooding current police flood. But I still do expect that our test will be on Monday. Okay, the first day of your coming back after semester break. So see you by then. If there's any update on midterm, I will update you on. Okay, any question? Any discussion? Nothing? Thank you very much. See you guys later. I think this video is also available in e-learning, but of course without my interruption. So feel free to revisit if you need them. Thank you very much. Assalamualaikum. I'm ending the call to everyone. Okay, thank you very much.